next I want to move into totally new territory now, and we're going to start talking about electrochemical cells. Basically, these simply are electrodes that are in contact with some electrolytic solution, and the chemical reaction either generates or uses electric current, which is electric current is nothing more than the flow of electrons from, well, we see it, right? It's the redox reactions. It's a flow of electrons from one atom within a molecule to another atom within another molecule, except this time we're going to separate the half reactions. Instead of them both occurring in the same beaker, we're now basically separating the two beakers, and we're going to make an electrical connection between the two. We're also going to make a chemical connection between the two as well. You have to have both, the electrical connection and the chemical connection. That'll become obvious once we get into it. So a voltaic cell, which is also called a galvanic cell. So a voltaic cell, a galvanic cell, a battery, they are all the same thing. Okay, there's absolutely no difference. I forget the history of why there's two terms for it, but you can have a voltaic cell, a galvanic cell, and a battery are all exactly the same thing. It's an electrochemical reaction that is spontaneous that generates an electrical current. Okay. So an electrolytic cell, again, is an electrochemical cell that's non-spontaneous. So in the case of an electrolytic cell, you have to force the reaction to occur. You basically hook a battery up to it or a power supply up to it, and you force electrons through the system to drive the reaction, the non-spontaneous reaction to occur. So we can construct a cell to physically separate the oxidation and reduction reaction into the two half reactions. So the force of the force with which the electrons travel from the oxidation half reaction to the reduction half reaction is what we call the voltage. So the voltage or the potential, again, mean the same thing. So voltage and potential mean the same thing. So here it is. We have two beakers, each contain a different electrolyte. You're going to be expected to know how to draw these voltaic cells. Again, make sure you're doing your homework. So let's say, for example, here I have an iron strip is this electrode and a solution of iron 2. So whatever it is, iron 2 sulfate, some soluble salt that contains the iron 2 ion. Then in the other cell, we have a copper strip, and then that's in a solution of copper 2+. So this was the same thing as me dipping the iron nail into the copper solution and that chemical reaction automatically happening. Now we're actually separating the two, okay? Now, on this side, we're going to have our oxidation, right? The iron's going to go from 0, its oxidation number is going to increase to +2, and it's going to release 2 electrons. Now, I don't care how you write these cells, but I personally always put the oxidation half reaction on the left and the reduction half reaction on the right. That way I don't confuse myself later on, okay? It's also in alphabetical order, right? This is the oxidation. This will be the reduction half reaction, where once the electrons released from this reaction will be consumed by this reaction to go from the copper 2+ to reduce it to the neutral copper or 0 valent copper. So there's our reduction half reaction. Now we need a chemical connection between these two solutions, and we call that a salt bridge. And that salt bridge generally just contains some benign salt, so it doesn't change the pH. So it's generally the cation of a strong base and the anion of a strong acid. Potassium chloride is most often used, but you could use lithium chloride, sodium chloride, you could use potassium nitrate, okay, so anything like that. But usually it is just potassium chloride. It's relatively cheap and easy to get. And this is basically a gel, okay? So this is just basically a gel, and it has a ton of the potassium chloride in it. And it is an aqueous gel, so therefore the potassium chloride is is separated into the potassium and chloride ions. The gel is prevented to leak out into the solutions. It's just literally you could use a cotton ball and stuff it up into this tube, because this tube does go into the solution. Okay, it's not closed at the end. There's just a cotton ball here to prevent the gel from spilling out. And that's what we call the porous plug. Okay, so what's happening? So here we have our iron, here we have our copper. Again, there's our iron electrode, our iron atoms, the individual iron atoms. There's our copper electrode and the individual copper atoms. Now in solution, what's happening is that, again, this is an oxidation half reaction. So the iron is given up 2 electrons. And when it does that, it separates from the metal, the pure metal, and goes into solution as a copper 2+ ion. Those electrons then pass through the external circuit and they go over to the reduction half reaction. So they go from the iron over to the copper electrode. When they come in, now the electrons sit at the surface due to the Faraday effect. So once an ion, in this case a copper 2+ ion, comes in contact with the metal surface, those electrons are transferred to the copper to form copper solid. So as time goes by, the iron electrode is disintegrating and the copper electrode is becoming bigger and bigger. Okay. Now, we got to think about this though, because I am losing electrons out of here. This is becoming more and more positive, right? I keep adding more and more positive ions to the solution. Well, that's an issue because the solutions have to be neutral. Everything in nature has to be neutral. So I must replace those negative charges that I keep losing. And that's where the salt bridge comes into play. In this case, since I'm losing negative charge, the negatively charged chlorine ions are going to migrate into the solution to keep this solution neutral. In this case here, I keep losing the positively charged copper 2. So again, to keep this solution neutral, the positively charged potassium ions are moving into solution. So the salt bridge keeps the solutions neutral. Okay, so that's the purpose of the salt bridge. So here it is, again, just a quick overview. So again, here we have the iron electrode where the electrons are being produced. They're traveling to the external circuit. We use those electrons. In this case, we're lighting up a light bulb, but it might be to power a battery, to recharge a battery, or power an electric motor, or a hair dryer, whatever it is. We're going to use the electrons. But whenever we're done using the electrons, they don't just disappear. We can't create nor destroy matter. So after we're done using the electrons, they then travel back to the reduction half reaction. So they travel back to the copper. So we call the oxidation half reaction, what happens there, we call that iron strip, that's the anode. So that electrode is called the anode. And where the reduction is occurring, this copper strip here is called the cathode. We say negative because that's where the electrons are coming in, and then this is positive because they're going down into the solution and releasing positive ions. It is removing the positive ions from the solution. Okay, so again, notice it's in alphabetical order. The anode and then the cathode. So that's why I always go left to right. Also, anode, oxidation, they're both vowels. Cathode, reduction, they're both consonants. So keep that in mind. You could keep the anode in the oxidation and the cathode and the reduction correct. Okay, and again, you should be able to draw this electrochemical cell just as it's shown here, and I'll show you an example of that. It's a real simple drawing. It doesn't need to be three-dimensional or anything like that. We'll do a few of those problems again, either later today or tomorrow. Okay, so now, as long as there's an external circuit, electrons can flow through it from one electrode to the other. And like we said, the iron keeps going from the solid into solution, so we can see that it's disintegrating over time. And at the cathode, right, the reduction, the copper ions are going from solution and becoming part of the solid copper. So we can see that the copper electrode, the cathode, is growing. Okay, it gets bigger in mass. Now, eventually, of course, we are either going to run out of copper ions in solution, and we could replenish them if we would like, or the iron electrode's finally going to completely disintegrate. And again, in either case, we're going to lose our electrical connection and we'll stop generating the electrical current. Okay, the way we measure these things is we simply use what's called a multimeter or a voltmeter, okay? And in this particular case, I'm showing you a picture of zinc solution with a zinc, this is the zinc electrode in a zinc solution, and this is just a copper in a copper solution, okay? And so we can see that the chemical potential of these two, this combination of copper and zinc, produces 1.08 volts. So it produces 1.08 volts. Now we're going to find out that each material has its own potential, and the current that it produces, the voltage that it produces, is going to be unique for the difference between those two unique materials. So again, just as a quick recap, the electrode at which the oxidation occurs is called the anode. Okay, the electrons are lost or released to the external circuit. And the electrode at which the reduction occurs is called the cathode. So this is the reaction that uses those electrons from the oxidation half reaction. Now the sum of the two half reactions gives the overall reaction, which we call the cell reaction. So the cell reaction is simply the overall reaction. And again, remember, galvanic and voltaic mean exactly the same thing, okay? Okay, now I want to talk about how we write this. Instead of drawing out that drawing every time, I do want you to be able to draw it out so you know physically what these electrochemical cells look like and how they work. But whenever we're working with electrochemical cells, we're not going to draw out the cell every time. We're going to use what's called a shorthand notation. The shorthand notation is going to show all of the species involved in the oxidation reduction reaction. And so, for example, we just seen this voltaic cell with the iron and copper electrodes. So the shorthand designation looks something like this. So our electrodes are always on the far left and the far right. So in this case, our anode, the oxidation, right, is going to be on the far left. Notice that there's no coefficients. Now I know there's no coefficients in this balanced chemical equation, but if there were, we do not include the coefficients in the shorthand designation, okay? So there will be no coefficients in the shorthand designation. And then, like I said, the other extreme, the right, is going to be our cathode. And that, of course, is our reduction half reaction. Again, the shorthand designation always has to be written in this way. The anode on the left and the cathode on the right. So that's why I say when you draw the cells, you should always draw them with the anode on the left and the cathode on the right. Okay. Again, if you're going to be a rebel and draw the cell the opposite way, I have no problem with that. Just be very careful that you get everything going, the electrons going in the right direction. You're labeling the cathode and anode correctly. Okay. But for the shorthand designation, you don't have a choice. It's got to be the anode on the left and the cathode on the right. This double line simply represents our salt bridge. Okay, that's separating the two cells. Now, this is a very simple cell. I'm going to show you a much more complicated cells where there's a lot of other things going on here, and we'll slowly build up to that. And then here, this is just representing whatever the electrolytic solution is, right? So there's our anode, cathode, and then these are the solutions. So we call these electrodes, we call them the cell terminals or electrodes, and that's why they are on the far left and far right of the shorthand designation, okay? A single line simply represents a phase boundary. So in this case, we have a solid and we have an aqueous solution. So the single lines represent phase boundaries. And again, we could have several lines on each side of these, depending on how complicated the cell is. Now, another thing to note too is that if we don't write a concentration beside our electrolyte, we are assuming that the electrolyte concentration is 1 molar. So that's the standard cell, right? So a standard cell, this would be 1 molar and this would be 1 molar. So if we don't write any concentration in the shorthand designation beside to the right of the ions, we automatically assume that the concentration is going to be 1 molar. So the iron's 1 molar and the copper is 1 molar at the start of the reaction. Obviously, as the reaction proceeds, the iron 2+ would increase in concentration and the copper 2+ would decrease in concentration. But for a brand new battery, you're starting out with those concentrations. Now, to measure each of the half reactions, we need a standard. We need somewhere to start. And to do that, we're going to use a special type of electrochemical cell that uses a gas. So in this particular case, this is going to be we're going to look at a hydrogen electrode, okay? So basically our electrode material this time is platinum. So that is the platinum. So that's either going to sit to the far left or far right of that shorthand designation because that's the actual electrode. That's where the electrons are being transported to the outside world, okay? In this case, again, we're talking about a hydrogen electrode, but it can be any gas. In this case, the hydrogen comes down a tube, and is bubbled across this platinum plate. Any excess hydrogen is just recycled back, okay? So, and then this is just 1/2 of the salt bridge, right? The salt bridge is simply going to the other half reaction that's sitting over here. So, like I said, the hydrogen is bubbling over the platinum electrode. That's actually where the chemistry is occurring. So what's actually occurring there, if this is the anode, so this hydrogen cell could either be the anode or the cathode. So if this is the anode, then the hydrogen bubbles across the platinum surface, is separated into hydrogen ions and electrons. The electrons then are free to pass through the circuit, and the hydrogen ions simply go into solution. So this solution, if this is an anode for the hydrogen electrode, this solution keeps becoming more and more acidic as the hydrogen ion concentration increases. And if it is the cathode, so if it's the other one, just the opposite happens. The hydrogen ions absorb to the surface of the platinum, electrons come in from the anode, the other half reaction, then recombine. The hydrogens recombine to form hydrogen gas, and so hydrogen bubbles begin to form off of the platinum electrode. So again, that's if this is the cathode. So again, this can act as either the anode or the cathode. It depends on the other materials in the other half reaction, the other half cell, okay? Okay, so the notation then for the hydrogen electrode would be written like this. So if it's the anode, again, here's our platinum electrode, a phase boundary with a hydrogen gas, another phase boundary because we have the aqueous hydrogen ion. And then this would be the salt bridge, and then this would be whatever the cathode of this particular cell is. And likewise, if it was the cathode, it would be just the opposite. Okay, again, the electrode's going to be way out here, followed by our gas, and then the aqueous solution. And the aqueous solution is always written beside the salt bridge because that's where the aqueous solution is in contact with, right? It's in contact with the salt bridge. The gas is in contact with both the platinum and the solution itself. So there's a reason why these things are put in this order, and you just need to think about it. That's why you need to physically understand what the cell looks like and know how to draw it, because then you'll be able to not only write these shorthand notations, but you'll be able to interpret them properly. Okay?
I have a quick question.
Yep.
To go back, because I understand when you say that the hydrogen gas is in contact with the platinum and the hydrogen, like the aqueous, like the solution,
Yep.
but wouldn't the platinum that's also within the water, or like the aqueous solution,
it is, but the aqueous solution has to be with the salt bridge, right? Because that's where that chemistry occurs. We got the ions from the salt bridge going into solution.
Okay.
Okay. And we always write the electrode where the electrons are going out to the far right. That forces us to put the hydrogen here.
Okay, so it's a matter of like they all connect, but what's more important?
That's right. Exactly. So the solution always has to be in contact with the salt bridge, and the electrode always has to be last because it's in contact with the outside world, that electrical circuit.
Okay, that makes sense.
Okay. Okay, so solution concentrations and gas pressures are going to be written in parentheses within the cell notation. So for example, it might look like this. So here I have a silver anode in a silver 1 solution, and that solution is 1 molar. Now, this could be 0.1 molar, okay? So again, if nothing's written, we automatically assume it's in 1 molar. We could also write the concentrations like this. So you'll see this oftentimes in electrodes, like in the pH electrode. You basically have a solution of a saturated salt. So in this case, it's saturated potassium chloride. Now, if it's a weak electrolyte, so if it's a strong electrolyte, we know that it completely dissociates, and we could actually calculate the concentration of it. If it's a weak electrolyte, again, we could still calculate the concentration of it, but it's usually an insoluble salt. And again, we'd have to use the KSP to calculate its concentration. And then if we have a gas, in this case chlorine, again, we're going to indicate the pressure. Now, the pressure of the gas is almost always 1 atmosphere. It's really whatever your atmospheric pressure is. So again, here in northern or central Pennsylvania, the atmospheric pressure is around 742 to 745 millimeters of mercury. So that's what it would be. But we normally just call it 1 atmosphere. It's whatever the atmospheric pressure is. Okay. So our gases are almost always at whatever the atmospheric pressure is. And that's for reasons of design of the cell. To make a pressurized electrochemical cell is very difficult and not necessary. So why do it? Okay. So generally our gases are always whatever the atmospheric pressure is. But if it wasn't, we would indicate what it is. Okay, now we went from a balanced overall cell reaction, right? So we went from the cell reaction to the shorthand form, but what if we want to go from the shorthand form to the overall cell reaction? Well, this is where the balancing comes back into play, okay? We got to separate them into the oxidation and reduction half reactions, which are already separated, right? So the silver and the silver plus 1. So would the oxidation be silver going to silver plus 1 or silver plus 1 going to silver? What would be that half reaction for the oxidation?
Is it +2?
No, I'm talking about the oxidation. Do we write this on the left and this on the right, or this on the right and this on the left for the oxidation half reaction?
Right.
Which one's going to be on the right?
The AG.
Right, just the pure silver, right? Because in an oxidation reaction, the oxidation number increases. So this has an oxidation number of 0. This has an oxidation of +1. So it's going to go from silver to +1. Now, we got to look at this. These, again, when we have gases involved, when we have more than one phase, you have to think more about how it goes. It's not necessarily in order, right? Here it was in order because it went from 0 to +1. But in the cases of this, sometimes it's in order. If it's a simple cell that just has metal ions in solution and a metal electrode, it probably already is in the correct order. But for gases, you got to be careful. So for gases, it's a reduction half reaction. The oxidation number is going to decrease. So here we have molecular chlorine, charge of 0, so its oxidation state is 0, and the chloride is -1. So for the reduction half reaction, we've got to reduce the oxidation number, so it's going from 0 to -1. So there's the reduction half reaction. And then we do what we normally do when we balance. We're going to balance all of the elements except for oxygen and hydrogen first, and then we're going to charge balance. So in the case of this reaction, we have one silver, so it's mass balanced. There's no oxygen or hydrogen. This side has +1, this side is 0, so I'm going to add one negatively charged electron to this side. Now it's a sum of 0 and a sum of 0 for the charges. Here I have 2 chlorine, only 1, so I'm going to put a 2 in front of the chloride. Now to charge balance this, I have a sum of 0 and a sum of -2, right? There's 2 at -1, so -2. So I'm going to add 2 electrons to this side. Now they're both mass and charged balanced. But to add these two reactions together, the electrons must cancel. So I'm going to have to multiply each of these coefficients by 2 so that I have 2 electrons in my oxidation and 2 electrons in my reduction half reactions. Later on, we're going to start introducing equations that involve these electrochemical cells. And we're going to talk about N, the number of moles of electrons that are being transferred from one half reaction to another. This is going to be the value of N. When the two half reactions can be added together so that their electrons cancel, that is going to be the value of N. So in this particular electrochemical cell, 2 moles of electrons are being transferred. So now to get the overall cell reaction, we're simply going to cancel out those 2 electrons. We would simplify anything else if we had to. In this case, we don't, so we simply bring down everything else. Notice that I wrote the platinum over the arrow because the platinum is just acting as a catalyst for this chemical reaction to occur. Okay? Now, a lot of times you don't have to use platinum. You could use different materials, but it generally does have an effect on the efficiency of the cell. Okay? Not necessarily the potential, but the current. So, multiplying the coefficients does not affect the potentials. Okay, that's going to make more sense here in a second. So the potentials of each of these half reactions, and remember the overall cell potential is going to be the difference between these two potentials. It's actually going to be the sum of these two potentials. The way we're going to use it is going to be the difference. I'll show you that in a second. But that voltage is not affected by multiplying the coefficients. So the electrochemical potential is an intensive property. Unlike most of our other properties that have been extensive, the electrical potential is an intensive property. So what we do to these coefficients will never affect the potential of our cells. So the electrical charge moves from one point of high electrical potential, okay, to a lower electrical potential. It's just like water, right? If you have a big barrel of water, and if it's sitting on the ground, the pressure inside that barrel is nearly 0, right? I mean, it still has water above it, so it will leak out if you put the hole at the bottom of the barrel. But if I raise that barrel, let's say 100 feet in the air, now all of a sudden, the pressure that's coming out of that barrel is much greater. Well, that's exactly the same thing that happens with these electrical potentials. The potential difference, which is measured again in volts, will become higher and higher as the potential between the oxidizing and reducing reactions becomes greater. Okay? So the work expended in moving the electrical charge through the conductor depends on the amount of charge and the electrical potential difference. Okay, so work done by voltaic cell. So work, in this case, can be represented by negative F, negative because the system is losing energy, right? We're losing energy, so that's where the negative comes into play. And then this is just a constant. That's called Faraday's constant. That is the charge on 1 mole of electrons. Okay, so that's the charge on 1 mole of electrons. And that's going to have units of coulombs. The charge on 1 mole of electron you can find by taking the charge on a single electron, 1.6 times 10 to the negative 19 coulombs, and multiplying it by Avogadro's number, 6.022 times 10 to the 23rd. That gives you this number here, 96,500 coulombs per mole of electrons. 96,500 coulombs per mole of electrons. That is a lot of charge. Okay, that would fry you in an instant. Okay. Okay, note that, and I just said that. Okay, and then this is the potential difference, which is going to have units of volts. So work, of course, has to be in joules. That's energy. So here's the relationship. 1 volt is equal to 1 joule per coulomb, or 1 joule is equal to 1 coulomb volt, however you want to look at it. Okay, so again, 1 volt is equal to 1 joule per coulomb, or 1 joule is equal to 1 coulomb volt. The coulombs and the volts are multiplied together when it equals 1 joule. Okay. The reason I give it to you this way is this is the most often way that we have to write this. Okay, so again, the volt is units of volts, but we could refer to it as joules per coulomb. You can see now that the coulombs cancel, and that would leave us with joules. Okay, next I want to talk about the electromotive force. So the potential difference, again, the voltage across the electrodes, is less than the maximum possible voltage of the cell during normal operation of the voltaic cell. Again, this would be the same thing like the water tower. If you put a pressure gauge on your faucet, and the pressure gauge is before the faucet, that pressure gauge is going to read, let's say you have really good water pressure, and it's 100 psi, 100 pounds per square inch. As soon as you turn on that faucet, that pressure is going to drop slightly. That's the same thing that happens with the electromotive force, the chemical potential, the potential difference in these electrochemical cells. As soon as you start using it, as soon as you start using that battery, the voltage is going to drop a little bit. Okay. So the flow of electrons during the use, again, is going to reduce this electrical pressure, just like it would, again, for a water system. So the cell voltage then has its maximum value when no current flows. And that's generally when we measure it, okay, when there's no current flowing. And how do we measure it? Again, we're simply going to use a multimeter. So again, we're just going to set it for measuring voltage, the potential. And again, in this case, it's 30.5 millivolts. Okay, so it's 30.5 millivolts. Now, our cell voltage is also called the electromotive force, or EMF, which is also represented by the variable E cell. Okay, now be careful, there's different E cells. This is E cell, and then if we put a naught here, we're going to call that the standard cell potential. So this is just the cell potential. This is what you would actually measure. The standard cell potential would be the cell potential without any kind of load. That would be our maximum. That would be the maximum potential, would be our standard cell potential.
Would that be a molar quantity?
No, it's just in volts.
Oh, okay.
Okay, it just has units of volts. Okay, so the cell EMF, again, is a measure of the driving force of the cell reaction. Okay, the reaction at the anode has a definite oxidation potential, while the reaction at the cathode has a definite reduction potential. In other words, each material has a very specific oxidation and reduction potential. Okay, now I know that sounds weird, but every material can either be oxidized or reduced. It simply depends on what the other material is. Okay, if the other one has a higher potential, then it is probably going to be reduced. If the other material has a lower potential, then it's probably going to be oxidized. So it just depends on what those potentials are. Now, again, we're not going to use this equation. That's why it's not in a blue bubble, okay? But the overall cell EMF is simply the sum of the oxidation potential plus the reduction potential. But we're going to find out that in the tables that list these potentials, it only lists the reduction potentials. So that's why I'm saying we're not going to use this equation. This is the real equation. The oxidation potential plus the reduction potential is equal to the cell potential. All half reactions are given, again, as reduction potentials. Okay, and again, that's basically a measure of the tendency to gain electrons in a reduction half reaction. Okay, so the oxidation half reaction is just the reverse of the corresponding reduction reaction, but you switch the sign. It's simply going to be the opposite sign. So again, the reduction potential, all we're going to do is flip the reduction, that particular reduction half reaction. If we flip it, reactants and products, we get the oxidation half reaction, and we simply flip the sign then of the reduction potential. That would give us the oxidation potential. So many standard electrode potentials are given as, again, reduction potentials, can be found in the appendix of your book, or of course in the tables of chemical data. So let's consider our iron copper cell again. So I could look up the two half reactions. Okay, so here's the iron. Now that is the reduction, right? It's going from, I'm sorry, this is the oxidation. It's going from 0 to +2. And this copper is the reduction. So it's the copper 2 plus going to copper 0. Now I have to look up in the book the reduction potential for the iron 2 plus. Again, they're only given as reduction potential. So I have to basically look for the opposite of this. I'm going to flip it. I'm going to take my products, they're going to become my reactants going to become my products, and so that's what I look up in the table. And it has a reduction potential of negative 0.45 volts. So if I flip this reaction, again, all I'm going to do is flip the sign. Okay? So it's the negative of the standard reduction potential. This would then be the oxidation potential. Now, for the copper, we're going to look it up, and it's already given as the reduction half reaction. So I'm just going to look up this chemical reaction in the table, and I'm going to find that its standard reduction potential is 0.34 volts. So now, if I have to get the overall cell, and these are both reduction potentials, since we had to flip it, we have this negative sign. So now we're going to rewrite it like this. We're going to say that it's always going to be the cathode minus the anode. And these are both reduction potentials. Okay, this is the way we're always going to do it, since we're always given reduction potentials. So it's going to be the cathode minus the anode. Notice that that's not in alphabetical order. That's the only thing in oxidation reduction that's not in alphabetical order. Okay, so again, So again, this arrow should be pointing to this. This is the reduction half reaction for the copper, and this is for the oxidation, but it's still the reduction. These are both the standard reduction potentials, okay? So that's going to be the 0.34 volts minus the 0.45 volts, and that gives us a cell potential. So notice it's a standard cell potential. This is at 25 degrees Celsius, 1 atmosphere if gases are involved, 1 molar for the ions in solution. Okay, so this is the standard cell potential, and it is 0.79 volts. Okay, any questions about that? Okay, so again, we have the anode, we have the cathode, and so the standard cell potential is just going to be the cathode minus the anode. Okay, so there it is, the cathode minus the anode. That's how we're going to determine the standard cell potential using the standard reduction potentials. Again, these are both the reduction potentials, even though this is oxidation, that's where the negative sign comes in. Okay, so the electrode potential then is an intensive property whose value is independent of the amount of species in the reaction. Okay, so again, that's why the coefficients don't matter. So if I have copper 2 plus going to copper, and it has a standard reduction potential of 0.34 volts, if I multiply each of the coefficients by 2, that potential remains the same. We don't do anything to it. The only time anything happens to this is if we flip this reaction. And again, we're not even going to worry about that, because to calculate the overall cell potential, we're using the equation that uses nothing but reduction potentials anyway. So we're never going to have to worry about doing anything to the reduction potentials. Okay, so again, intensive property. So multiplying these coefficients has no effect on the electrical potential. Okay, so the standard EMF is, again, the EMF of the cell operating under standard conditions. So 1 molar for solutions. If there's gases, 1 atmosphere, and the temperature is going to be at 25 degrees Celsius. Note that individual electrode potentials require that we choose a reference electrode. So this is just some arbitrary electrode that we're going to use for all other materials. And we chose the hydrogen electrode for that. So all of the cell potentials in those tables are based off the hydrogen electrode. Okay, so we could have the hydrogen. So basically what we're saying is that so here we have it going from +1 to 0. So this is the reduction. So we're saying the reduction standard potential is 0. So we just arbitrarily said that it is 0, and we're going to base everything else off of that. So we're going to test all other materials using the hydrogen electrode. So any cell potential that's generated, that will be the reduction potential for those problems. Yes, we will be talking about non-standard conditions where the concentrations are all changing. We're going to do that later on. Okay, so again, we're going to base all other of the reduction potentials off of this hydrogen electrode. So we arbitrarily set it to 0 volts. So again, if we measure a hydrogen electrode in one cell and aluminum and aluminum 3 plus in another cell, and we hook it up to a multimeter, that multimeter is going to read 1.66 volts. Okay. Now we can see that the aluminum is going from 0 to +3, so it's being oxidized. But this is what we get when we hook it up to the hydrogen electrode. So we're going to read 1.66 volts. That tells us, so another thing that we're going to find out too, is that for these chemical reactions to be spontaneous, the overall cell potential must be positive. So that's how I know that when I hook this up to a hydrogen electrode, this comes out to be positive. Therefore, I know that the aluminum, this must have been the oxidation half reaction. This must have been the anode. And therefore, the hydrogen electrode was acting as a cathode. This is the oxidation reaction. So in the table, though, it's going to be written as the reduction half reaction. So it's going to be listed in the table as aluminum 3 plus 3 electrons go into aluminum at negative 1.66 volts. So again, it's always going to be listed as the reduction half reaction. So here's an example of the table. We have lithium has a standard reduction potential of -3. Aluminum has a reduction potential of -1.6. Iron, -0.45. There's our hydrogen. It's at 0, right? That's what we used. The copper, on the other hand, has a positive value of 0.34. Oxygen reacting with acidic protons to form water is 1.23. Fluorine gas reacting with electrons to form the fluoride ion, 2.87. So the standard reduction potentials represent how easily electrons are picked up. So it makes sense, right? The nonmetals always form anions. The nonmetals always form anions. So you would expect their reduction potentials to be very large positive numbers. Metals, on the other hand, they don't want to pick up electrons. They want to give up electrons, right? They want to go from lithium to lithium plus. So notice that its reduction potential is negative, meaning it's not favorable, and it's very high. The more that particular element wants to give up electrons, the more negative the standard reduction potential is. Now remember, we could look at this in the opposite direction too, right? We could look at the oxidation, where we would flip every single one of these reactions, and then we would flip every one of these signs. That again would make sense. For oxidation, they're giving up the electrons, so the metals would have the highest, most positive values. So you can see how it goes back and forth between oxidation and reduction. So again, listed as reduction potentials, the more positive and the greater the value, the easier it is for that particular atom, molecule, or element to pick up electrons. Okay, next I want to talk about oxidizing and reducing agents. So this is just a review from Chem 110. So again, an oxidizing agent causes the oxidation of something else, and it itself is reduced. Okay, so in this case, the copper 2 plus caused the oxidation of iron. Iron went from 0, it was oxidized, to 2 plus. Its oxidation number increased. And the copper 2 plus itself then was reduced to copper 0. So again, an oxidizing agent is one that oxidizes another species, and it itself is reduced. So therefore, the copper 2 plus is the oxidizing agent. Again, it caused the oxidation of the iron from 0 to 2 plus, and it itself was reduced from copper 2 plus to copper 0. The reducing agent causes the reduction of something else, and it itself is oxidized. So the iron caused the reduction of the copper 2 plus. Its oxidation number was reduced, okay? So it caused the reduction of something else, but it itself was oxidized. It went from 0, its oxidation number increased to +2. So therefore, the iron would be the reducing agent. Okay? Any questions about that? Now be careful with this. Students oftentimes get these two backwards. Remember, an agent does something for somebody else. So if it's a reducing agent, it reduced something else. So standard electrode potentials now are going to be very useful in determining the strengths of oxidizing and reducing agents under standard conditions. Okay, So again, a reduction half reaction has the general form. We have the oxidized species picking up electrons to become reduced. And the oxidized species then acts as the oxidizing agent, right? It caused the oxidation of something else and it itself was reduced. Consequently, the strongest oxidizing agents in the table of standard electrode potentials, remember these are reduction potentials, are the oxidized species corresponding to the most positive standard reduction values. So that means F2. So fluorine is a really, really good oxidizing species. So is oxygen. Really, really good oxidizing species. Okay, an oxidizing agent. And vice versa, so an oxidation half reaction has the general form of a reduced species giving up its electrons to become an oxidized species. So the reduced species acts as a reducing agent, right? So this acts as a reducing agent, causes a reduction of something else, and it itself is oxidized. And again, the most negative values are going to be the strongest reducing agents. So, for example, lithium had the most negative value. Therefore, lithium would be the strongest reducing agent. So there are a few equations that you need to know for this chapter. We've talked about one of them so far, and that one was to calculate the standard cell potential. So the standard cell potential, which is E cell naught. Again, remember, E cell without the naught is the actual potential of that particular system, that voltaic cell, that galvanic cell, that battery. This is the standard cell potential. This is, again, solutions being at 1 molar, pressures at 1 atmosphere, and temperature of 25 degrees Celsius. We can calculate that using the standard reduction potentials. So it's going to be the standard reduction potential of the cathode minus the standard reduction potential of the anode. Okay, and again, these are both reduction potentials, standard reduction potentials. Okay, so even though we know oxidation is occurring here, we're still going to use the reduction potential, and that's why we put this little negative sign right there. That was flipping the sign of the reduction potential. Okay, then it wants us to write the shorthand notation for the voltaic cell that is described by the following chemical reaction, and it also wants us to calculate the standard EMF. So to write the shorthand notation, right, it has a bunch of straight lines and double lines. So for example, what does the double line represent?
The salt bridge.
That's the salt bridge. So that's the middle of this reaction. What goes on the left side?
The oxidizing.
Okay, the oxidation half reaction. And what goes on the right side then?
The react.
The reduction half reaction. Okay. What is the electrode at the oxidation half reaction called? Is this a vowel or consonant? Is O a vowel or consonant?
It's the anode, right?
It is the anode, another vowel, right? So the anode. Notice that O comes before R in the alphabet. What is the electrode at the reduction half reaction called?
Cathode.
The cathode. Again, notice A becomes before C. This is a consonant, this is a consonant. Okay. What is my anode? What is being oxidized? Is chromium or mercury? So what would you have to do to determine that?
Get the oxidation numbers.
Right, so we're gonna have to assign oxidation numbers to everything. What's the oxidation numbers on chromium?
0.
Yeah, the charge is 0, right? So it's 0. What is the charge? What is this called? This is actually a polyatomic ion that you should know.
Mercury?
It's not just mercury.
Wait, there's two. Wait.
This is a polyatomic ion. Hannah, you've asked me about this in the past.
It's mercury 2.
It's not mercury 2.
It's not mercury 2.
Mercury 2 looks like, mercury 2 is this. That is a monatomic ion. It's not polyatomic. So what's this called?
Dimercury? No.
No. Let's look at it this way. There's 2 mercuries. Oh, shit. There's 2 mercuries. What's that going to equal? If this is the oxidation number of mercury,
Mercury 1.
what is the charge on this polyatomic ion?
+2.
Plus 2. Divide through by 2. The oxidation state of this mercury is mercury 1. It's +1. This polyatomic ion is called mercury 1. That's why it's called mercury 1. So it's +1. And again, remember, there's 2 of them, but I don't care. We're assuming that all the elements, all the atoms of a given element have the same oxidation number. Okay, what's the oxidation number of this?
+3.
It's a monatomic ion. 1 atom with a charge. Charge equals the oxidation state. What's the oxidation state of this?
Zero.
Yeah, there's no charge here, right? It's 0. Okay, so what was oxidized?
The chromium.
Yeah, right. The chromium, the oxidation number went from 0 to +3. So in other words, the chromium went from 0 to +3. So what do I write over here then? For the shorthand, what goes farthest to the left?
The one that's closer to the outside.
That's the one that I can hook an alligator clip to, right? That I can make an physically make an electrical connection to. I can't make an electrical connection to water, right? So what's that going to be?
Chromium.
That's going to be the solid chromium. Then what does this line represent?
A phase change.
A phase boundary, right?
Okay.
So that's a solid. So then what's going to go here?
Chromium the aqueous.
Yeah, the aqueous chromium 3.
3+.
Now, normally we put the concentration. So what's the concentration going to be here, assuming we have a standard cell?
1 molar.
That would be 1 molar. Then the other one must be the mercury. So we have the Hg 22 plus going to Hg. Now there's 2 of them, so I'd have to put a 2 here. And if we were to charge balance, I'd have to put 3 electrons here and then 2 electrons over here. So what's going to go on this side then?
The 2 electrons plus the mercury 1.
No electrons go into shorthand form.
Awkward.
What am I going to put right here, right on the other half of this salt bridge? What am I going to, mercury 1, okay? And again, if this is a standard cell, we would say it's 1 molar. Then a phase boundary, then what? Well, it has to be the mercury, right? Now, the weird thing is that mercury is actually a liquid. So in this particular, now I would expect you to give me this, but in reality, if I ask you to draw a cell that has mercury, well, that cell, in this case, right, that cell looks like this. We have our salt bridge, which is going over to the other cell. In this case here, I'll just draw it real quick, right? So there's this cell, and this salt bridge is going into here. This electrode, well, this electrode is in a solution that contains chromium 3 plus, and this thing here is a chromium electrode. It's a solid. But in this case, we'd have a solution that had the mercury 1 in it floating around, but mercury is a liquid itself, and mercury is going to be laying at the bottom of this because it is so much more dense than water. I can't hook an electrode up to that. So what you would do in real life is you would take another metal, platinum or copper. Copper works really well. And you would simply stick a piece of copper into the liquid mercury. Okay. So this is liquid mercury. And the reason you would use platinum or copper or gold is because these things have positive standard electrode potential. So they're not going to react. It's going to be the liquid mercury that reacts. So this would just be your copper electrode. So the reality is there would be one more here and would say it was copper. In this case, the copper, again, is just acting as a conduit for the electrons between the liquid mercury and the outside world, right? Because then this would go to some external circuit, would light up a light bulb. The electrons are going to flow from the oxidation half reaction, where we're giving up electrons, and then back into the reduction half reaction where we're using those electrons. I'm sorry, I don't think you saw anything I just drew. Make sure that when I do that, please tell me to lift my paper.
I have a question.
Yep.
In that case where you would have the copper, in
Yep.
the balanced equilibrium equation above, would it show in the products as that being a thing, like there, or is it like an outline?
I'm sorry, what do you, I'm missing something. Notice that there's no coefficients in the shorthand.
No, I mean, not in the shorthand. I mean, in the equation above.
This one.
Yeah,
This ends up being the balanced equation, right? Because I had to multiply this through, right, by 2 and 3. That's why we end up with the 3 and the 6.
Oh, no, that's not my question. My question is, in reality, in like a real life situation where you have
This cell.
Yeah, and you have that copper.
Yep, that's going into the liquid mercury down here.
Because it's not like something that's being formed, it's something that you added. In the equation above, would it appear there?
Copper's not going to appear because no chemistry occurs.
Okay.
All the copper acts is it's taking the electrons. So it's bringing, in this case, we could see that it is bringing the electrons in.
Mm-hmm.
It's going through the copper. And then the electrons then sit on the surface of the mercury. Then the mercury 1 comes in and then reacts with the electrons to go from mercury 1 to liquid mercury. So the amount of mercury liquid keeps increasing as the reaction proceeds, and the chromium starts to deteriorate. So this increases and the chromium decreases.
Okay, I see.
Chromium electrode.
Yeah.
So the concentration of chromium 3 plus increases, and the concentration of mercury 1 in solution decreases because it's being consumed. Does that all make sense?
Yeah.
Okay, now the other part of this asks us to determine the standard cell potential, and we've seen that the standard cell potential is given by this this equation, where it says the standard reduction potential of the cathode minus the standard reduction potential of the anode is going to be equal to our standard cell potential. So what chemical equation am I going to look for the chromium part of this? So I'm going to look in a table of chemical data, and I want to know what reaction am I going to be looking for in those tables. Is this a reduction or oxidation half reaction?
Oxidation.
That's oxidation. So to make it a reduction half reaction, what would I have to do?
Flip it.
Flip it, right? So when you look in your tables of chemical data, okay, I have to look for the opposite of this reaction, which is right here. Right? It's the chromium 3 plus 3 electrons going to chromium solid. So it has a negative 0.73 reduction potential. Now be careful, because there's other things. Here's chromium 3 plus 1 electron going to chromium 2 plus. That is not that reaction. So make sure you're looking up the right reaction. It's got to be exactly this, except reversed, because it's a reduction. Okay, so the reduction, so these are the reduction standard potentials, which normally we just write like this. I'm just going to write RED just to reinforce the fact that these are reduction potentials, and they do have units of volts. So the chromium 3 plus 3 electrons going to chromium has a reduction potential of negative 0.73 volts. Now, what would I look up for the mercury, for this one? What would I look up? What chemical reaction?
That one exactly.
That one exactly, right? Now remember, the coefficients aren't going to be there. So you're not going to find 6, 3, 6. You're going to find the smallest whole number ratio for your coefficients. So that's why I wrote them the way I did, okay? So that you know that you're just looking up that, the simplified version. Okay, so when you look up the mercury, then that is going to have a standard reduction potential of plus 0.8 volts. So we're going to take the cathode. The cathode, again, the cathode was the mercury, so that's the 0.8 volts. And we're going to subtract from that the reduction potential of the anode, which was the chromium, so that's negative 0.73 volts. Negative is positive, so that's going to give me a value of 1.53 volts. Now again, I'll stress this again later, but when we have a positive cell voltage, we have a spontaneous reaction. This would be a battery or a voltaic cell or a galvanic cell. Again, they all mean the same thing. If this is negative, it's a non-spontaneous reaction. It will not be a battery, a galvanic cell, or a voltaic cell. However, if we force that reaction backwards by applying a greater potential, we then have what's called an electrolytic cell. So if this is positive, we have a spontaneous reaction. If it's negative, we have a non-spontaneous reaction. We're going to use that idea when we're trying to figure out what is going to be an oxidizing and reducing agent. Okay? Okay, any questions at this point in time? Please make sure you're doing your homework problems. I will be opening another quiz today at some point in time. I'm not sure if it'll be 1 or 2, depends on how far we get today. Okay. Okay, so number 75 says a voltaic cell is constructed from solutions of tin 2 chloride and gold 3 nitrate, along with tin and gold electrodes. The salt bridge contains saturated potassium nitrate gel, and it wants you to draw a completed diagram of the electrochemical cell. So first it says indicate the cell EMF. So basically I have these two, right? So what would my half reactions for this cell be? And I want to write them both as reduction potentials at first. So what would be my half reactions? And I want to write them both as reduction potentials. And you'll see why here in a second. You'll need to do the same thing. You'll need to write them both as reduction potentials at first. So what do you think? Kaylee, what do you think? What's one of my half reactions? Well, let's just look at this. Tin 2 chloride. What's going to happen to tin 2 chloride if it's in water?
It'll dissociate.
Okay, so you're saying it's a strong electrolyte? Because we know that chloride, salts, bromides, and iodides are soluble with the exception of silver, mercury, and lead. That's not an exception, so that's going to dissociate into tin 2 plus and a couple of chloride ions. Could we, so now could you tell me which one of the half reactions are going to be in the cell?
I'm not sure.
Hannah, can you tell me?
Would it be the SN2 plus going to the one with no charge? So
Okay, so it's neutral tin, right? So you're saying it's tin 2 plus going to tin, right? Because this is plus 2 going to 0, so that is reduction. Is this balanced?
no, there'll have to be 2 electrons on the side of the SN2 plus.
Exactly, right? So it is mass balanced. There's 1 tin, 1 tin. There's no oxygen or hydrogen to worry about. So this is just going to be plus 2 electrons. Now we have a sum of 0 equals 0. Okay. So, Katrin, what do you think the other, again, I want it as a reduction half reaction. What do you think it's going to be? Well, what's this? What's going to happen to the gold 3 nitrate? Taylor, what do you think? Yeah, I think we lost Katrin. I think she froze.
Is it going to dissociate as well?
Well, according to the solubility rules, what happens to nitrates?
Oh, NO3. That's soluble.
Yep.
So it's gonna go to and that's AU plus to NO3 3 minus.
Nope.
Is it 3 NO3?
Okay. What's the charges?
AU is +3, and then a minus on NO3.
Right. So what do you think the other reduction reaction is going to look like?
Would you do the AuNO3 going to AU3+?
Okay, but we're going to ignore the spectator ions. Okay, because they're not really doing anything in an electrochemical cell. They're just there. So it's just going to be the AU3+ going to AU. Okay. And then how do I balance this?
Do you add 3 electrons?
Yep. Right. So now we have 0 and 0. Phase labels, right? This would be a solid, because those are our metals. And then these are aqueous solutions. Okay. So now it's asking me for the cell EMF, and it says assume standard conditions. So what variable would that represent? Can anybody tell me what variable the cell EMF under standard conditions is?
E cell naught.
Yeah, right. So it's E cell naught. What's the equation for E cell naught?
E cathode minus E anode.
Yeah, right. And these are the standards. And what do these values represent? Are they reduction potentials? Are they oxidation potentials? Are they overall cell potentials?
Both of them are reduction.
They're both reduction, right? So that's why we wrote them both as reduction. So then you're simply going to look up these values, which are in volts, in the table. And this is exactly the equations you're going to look for. So the tin is negative 0.14 volts, and the gold is positive 1.5 volts. So how is this going to help us determine which one is the cathode and the anode?
Wait, I have a quick question.
Yep.
Going back, this is whenever you're writing the half reactions, how do you know which ones are the spectator ions? Like, how do you determine that?
Well, you had a tin electrode, right?
Yeah.
So what would have been important?
Oh, then just the
Tin,
tin.
right? And again, notice that this is the conjugate base of a strong acid. It's
Yeah.
not going to hydrolyze. There's nothing else for it to react with. Okay.
Mm-hmm. Okay. Thank you.
Okay. Okay, so everybody good with that? Okay, can anybody tell me why I did this? How is this going to help me determine which one is the cathode and which one is the anode? Because it never told you.
I feel like it has something to do with the fact that potassium nitrate is the gel, but I just don't understand the
Nope, nothing to do with the potassium nitrate.
Okay, cool.
It has to do with this value. Remember, we're creating a voltaic cell or a galvanic cell or a battery. Remember, they all mean the same thing. What has to be true about this value for a voltaic cell?
That value needs to be positive.
It has to be positive. Therefore, which one's my cathode?
The gold.
the gold, right? So this must be the cathode. And this must be the anode then. Because that gives me 1.5 volts minus negative 0.14 volts. That negative negative, of course, makes it positive, and so that's going to be 1.64 volts.
Wait, really quick, where did those values come from? The negative 0.14 and the 1.50?
That just comes from your tables of chemical data. Okay. I actually printed out new ones. So there it is. There's just all kinds of different ones. Okay. And again, on the final, these tables are much smaller. So if you are able to print out the thing that I'm going to give you, it would make it much easier for you. So basically, you're just looking down the line here. I see tin 2 plus, right? And then I can't get enough room here. Here's tin 2 plus, and you just follow it over, and it's at negative 0.14. Does that make sense? So again, these are just the standard reduction potentials. Okay. So that's where those values, so when I talk about these standard reduction potentials, that's where I'm getting them, from the tables of chemical data. Okay. Okay, does everybody get this point? Okay, at least a third of the students will write this backwards. But remember, this has to be positive to be a voltaic cell, a galvanic cell, or a battery. Okay. Okay, so everybody's good. Okay, so what is undergoing oxidation?
Gold.
I'm sorry, I didn't.
The gold would be going under oxidation.
So gold is undergoing oxidation.
Wait, no.
I want you to think about alphabetical order, and I want you to think about vowels matching vowels and consonants matching consonants.
So the anode is the oxidated, and then
That's
cathode
right.
is the least.
So anode, oxidation, right? They're both vowels. And so this isn't really what's happening, right? It's the opposite. It's the tin going to tin 2 plus the 2 electrons. Okay. And then what's happening to cathode, which would be reduction, right? So again, consonant, consonant, reduction. That's how you remember them very easily. So what chemical half reactions occurring for the reduction? What species is being reduced? What would that look like? Katrin, what would that look like?
That would be pretty much the same reduction or the same reaction we did above
For
gold.
For gold, right? So yeah, it's exactly, that was the reduction half reaction. So it looks identical to what we just wrote. Okay, any questions on that? Again, remember, both vowels, both consonants, that's how you keep them straight. Now the balanced overall reaction. Kaylee, how am I going to get that? How am I going to get the balanced overall reaction?
Would you include the gel in this one?
Nope. You guys like your gel. Think of it, it's the balanced overall reaction.
So you would combine the two equations that we have.
Two half reactions, right? Remember, these
Yeah.
are half reactions.
Okay.
Right? Half reactions. Okay, so can I just combine them then?
No.
Why not? What has to happen to combine those two reactions? What has to happen?
They have to have the same number of electrons.
Okay, so how am I going to do that? Because they don't. This one has 2, this one has 3.
I forgot how.
Hannah, what am I going to do?
You'd multiply the oxidation by 3 and the reduction by 2.
Right, right. So I'm going to multiply each of the coefficients by some factor so that I have a common denominator between the two. And in this case, right, it's going to be 6. Again, if you can't think of what it is, you could just, if this is 3, I can multiply this by 3. And if this is 2, I'll multiply this by 2. Now, you might have to simplify in the end if there is a lower common denominator. In this case, there isn't. 6 is the lowest common denominator between 2 and 3. So now, okay, Hannah, how did multiplying the tin by 3 affect its reduction potential, or in this case, oxidation potential?
It doesn't. It's an intensive property.
That's right, right? So these potentials are intensive properties, so it doesn't matter what you do to the coefficients. What about flipping the reaction? What happened to the potential when I flipped it? Did anything happen to the potential when I flipped this reaction?
It would have been negative, or negative to positive, or positive to negative.
Right, right. It was negative 0.14. When we flip it, we then have the oxidation potential, which is the opposite of the reduction potential. But again, I don't want to confuse you. These are both reduction potentials. Even though we know oxidation is occurring at the anode, in this equation, these are both reduction potentials. Okay, so now multiply through, so I have 3 tin solid going to 3 tin 2 plus 6 electrons. And then for the other one, I have 2 gold 3 plus 6 electrons going to what? 2 gold solids. Okay, and now I can add them because the electrons are going to cancel, and I'd simply bring down what was left. And there would be my balanced overall equation. Any questions about that guy? Okay, next it says, basically this is all going to be drawing the electrochemical cell. So to draw the cell, just draw 2 beakers, okay? Like that. Each beaker is going to have an electrode of some sort, okay? There's going to be a salt bridge that goes from one beaker to the other beaker. And then there's going to be an electrical connection to some kind of load to the other. These are going to be aqueous solutions. This is our salt bridge. And what is in the salt bridge? What is in my salt bridge?
The potassium nitrate.
There we go, the potassium nitrate. So KNO3. Okay. So it says, write the symbols of the elements and ions in appropriate. Now, again, I strongly encourage you to do the same, draw it the same way every time. And again, I would encourage you to do it in alphabetical order. That way nothing gets messed up. I'm going to make this the anode over here, and this is going to be the cathode over here. So if that is the anode, then what is the anode made out of? What is
Tin.
my, say again?
Tin.
Tin, right? We said the anode was our tin. So this is tin. That's our solid tin. And what's in this solution then?
The tin ion.
Yeah, right. Again, this is our half reaction, so that's what's in there, tin 2 plus. Okay. And then what's my cathode?
That'd be gold.
That is gold, solid gold. And in solution?
Gold ion.
Yeah, the gold 3 plus. Okay. So we did that. Identify the anode and cathode. Well, again, we're going to do that right off the bat. I'm going to say that's the anode, that's the cathode. Okay. It says write the appropriate half reactions under the cells. Now, you could give me either the simplified one or the balanced one. I don't care. But what would I write underneath the tin 2 plus? Well, just this reaction, right? It's an oxidation. Or again, you could write it as this. I don't really care if you give me this one or this one. It doesn't really matter. Okay. So I'm just going to write the simple one. So that's our tin solid going to tin 2 plus 2 electrons. And then the reduction, right, was just the reduction that we had written before. That was the gold 3 plus 3 electrons going to solid gold. Now, the reason I want you to write these underneath each one of the beakers is because the next one says, this is to help you answer the next two questions. It says, indicate the directions of in which the electrons are flowing. So are the electrons going from here to here or from here to here? Look at the chemical reactions. Which way are the electrons flowing? From left to right or right to left?
Right to left.
Right to left, so from here to here. But look at this here. They're being produced here, and then they're being consumed here.
Okay, so left to right.
Yeah, right. So the electrons are traveling this way. And this is my load. And what is the potential on my load? How many volts am I supplying to my load?
E cell naught.
Yeah, right. E cell naught, which we calculated is 1.64 volts. Okay. And then it says indicate the direction of ion flow. So this is a strong electrolyte, right? It's a strong electrolyte, potassium nitrate, rule number 1 and 2. So potassium and nitrate. So which way is my potassium flowing?
Is potassium going towards the cathode?
I'm sorry, you have the wrong number. I'm sorry, say it again.
Is potassium going towards the cathode?
So the cathode, so the potassium is
Towards
going
the right, yeah.
Yeah, right. We're losing gold 3 plus, so we got to replenish it. So the potassium is going into solution, right? So this is my potassium ion, if you can actually see that. So that's my potassium going into solution. And then over here, we have the nitrate going into solution because we're losing negative charge and gaining positive charge, right? So to replace that negative charge that we're losing, we got to put the NO3 minus into solution. That way, both solutions are remaining neutral. Okay, again, that's why I want you to look at these chemical reactions and you can tell the direction of electron flow and which way the ions are flowing. Okay. Okay, so now we want to write the shorthand form, right? So we had our overall reaction, and I want to know what the shorthand form then is going to be for this. So what can we start with? I want you to start in the middle. What would I put in the middle?
Double lines.
Yeah, and what do they represent?
I think like solution barrier.
It's the salt bridge. Okay, so that's the salt bridge between the two. Then what am I going to write on the left? What goes on the left? Just generally for any cell, what goes on the left? For any cell, what goes on the left? Again, it's really easy if you keep everything in alphabetical order. What goes on the left?
Anode,
Yeah. What goes on the right?
cathode,
Cathode. Okay. So, Kaylee, what would I actually put over here? What's going to go to the farthest to the left? And this again, for just generally, what goes farthest to the left and farthest to the right? It's going to be the electrodes, right? It's going to be the things that we hook up to the external circuit. So what goes farthest to the left then?
the tin, the solid
The
tin.
tin, right? So the solid tin. And then what?
Would it be the tin 2 plus?
Where's that go?
It goes next to it.
Right here. Okay. Am I missing anything?
Is there supposed to be a single line between them?
Yep. And what does that single line represent? Just a phase boundary, right? We have a solid and an aqueous solution. Okay. Taylor, what do you think goes on the right then?
Would it be 2 AU solid?
Okay, we don't notice, there's no coefficients. We never put coefficients in the
Oh,
shorthand
okay.
term. So where does the AU solid go exactly? Right here?
Oh, would it be on the right side?
The far right, right?
Yeah, the
Again, that's what we're hooking up our alligator clips. That's where we're making our electrical connection. So what else do I need to do?
and then on the far left, put AU 3 plus.
To the far left or to the left of this? Here or here?
Oh, to the left of the solid.
Okay, so AU3 plus. Anything else?
Would you put a line between those as well?
Okay. Now, we don't have to write anything else here, but sometimes we do. What else?
Question.
Say again?
What did you say the single line represents again?
A phase transition.
Oh, okay.
In other words, this is a solid, it's a separation of phases. So this is a solid and this is an aqueous solution. Okay. Now there's something else that we sometimes have to add to these shorthand representations. Does anybody remember what they are? What that is? So normally we put the concentrations beside the aqueous solutions, right? In this case though, what is the concentration of tin?
It's standard, so it's 1 molar.
It is 1 molar, and so will be the gold. Otherwise, we would put the non-standard concentrations. If we don't put anything, we're automatically assuming standard conditions, which would be 1 molar. 1 atmosphere for gases, all 25 degrees Celsius. Okay, any questions about drawn an electrochemical cell? Okay. Okay, let's try another. So this will be number 37 out of chapter 19. And it says, do you expect the following reactions to occur spontaneously under standard conditions? Use standard electrode potentials to answer these questions. So it says, will iodite, IO3 minus, oxidize chloride ions to chlorine gas in acidic solution? So how would you go about answering these questions? So how would you go about answering these questions? Take a wild guess.
Would you just see that the iodate ions are going to form a gas and assume that that would be spontaneous?
Well, no, because you'd just be talking about the system.
Oh.
It's a change in entropy of the universe that tells you whether something's spontaneous or not. Okay.
Oh.
We'll come back to that. That's going to be a second way that we actually look at it, is the spontaneity of the reaction. But I want to just answer it basically the way it asks here. It says use standard electrode potentials. Well, where do I get standard electrode potentials? Where do I get them? Kaylee, I'm specifically asking you, where do I get standard electrode potentials? I'm specifically asking you because you specifically asked me earlier.
The tables.
The tables of chemical data,
Yeah.
right? Okay, so I'm going to look in the tables of chemical data. So here we go. And I'm looking for IO3 minus. So I'm just looking here, any IO3 minuses, and it could be in reactants or products. right? So I'm just going down. So this can be the tough part, especially when you have huge tables. That's why it would encourage you to print out the tables that I normally use for the finals. So I see no IO3 minus there, and I keep looking. Here's an IO3 minus. So here's one here. I want to look, because sometimes there's more than one. That's the only IO3 minus I see, is that right there. Okay. So that is, so if I just rewrite that then, that is IO3 minus plus 6H plus 5 electrons going to 1/2 I2 aqueous, which I'm going to ignore the phase labels, they're irrelevant here, 3H2O, and it has a standard reduction potential of positive 1.2 volts. Now I'm going to do the exact same thing for the chlorine, right? So now I'm going to go down and I'm going to look for the chlorine. Now, if you do this is more of an educated guess, I would say, would you expect the chlorine to be more negative or positive? Would you expect chlorine to have a negative or a positive reduction potential? Well, there's the lithium, right? Lithium goes to lithium solid. And then at the very other extreme, we have fluorine. So we have the fluorine. Oh, shoot, I wanted to leave room for this. So the reduction potential for these guys, so for the lithium, it was negative 3.04 volts. And for the fluorine, it is positive 2.87 volts. Now, remember, these are reduction potentials, right? So the fluorine was reduced and the lithium is being reduced. So I can tell by the positive, remember, spontaneous means positive, right? In the case of our standard potentials. So positive. So that means that fluorine likes to pick up electrons to form fluoride. Metals don't like to pick up electrons. They like to do just the opposite, right? They like to give up electrons. And that's why this is a large negative value. So before I even look at the tables, in this case, we're looking for chlorine, right? Chlorine gas and chloride ions. Would I expect that to be a positive or a negative value?
Wait, I have a quick question. Where did the lithium and fluorine come from?
You see that?
Yeah, but what, like, why did you choose those?
I'm just talking about this. I'm sorry. This is totally separate from
Oh,
this
okay.
problem, okay?
Alright.
I'm trying to get you to understand what these values mean.
Okay.
You need to understand these values to answer these questions.
Okay, gotcha.
So if I'm looking for chlorine in those tables, would I expect the value to be negative or positive? Remember, we're always looking at reduction.
Chlorine would be a non-metal, so
Yep.
we would expect it to be positive.
Exactly right. It likes to pick up electrons. Non-metals like to pick up electrons, so it's going to be spontaneous. It's going to be a positive potential. Metals like to give up electrons. So it accepting an electron is going to be non-spontaneous. It's going to be negative. Now remember, when I talk about spontaneity, for E, positive means spontaneous and negative means non-spontaneous. Just the opposite, of course, of del G. Okay, so I expect it to be positive. So I could jump to the bottom of my list and save myself a whole lot of time because I know it's probably going to be positive, and I'm just going to start from the bottom and go up. Oh, there it is. There's my chlorine gas. Okay, so there it is. So I could write that down now. So that's going to be Cl2 plus 2 electrons going to 2Cl minus. And that has a standard reduction potential of plus 1.36 volts. Okay, so again, that just came from the table of chemical data. Now it says, will iodate ions oxidize chloride ions to chlorine gas? So in other words, the question is asking, will this happen, right? So the question is asking, will that happen? So we're talking oxidizing. So we want to know which one is the stronger oxidizing agent. Now remember, the oxidizing agent causes the oxidation of something else, and it itself is reduced. That's exactly what we see here, the reduction reaction. So the one with the most positive reduction potential is going to be the strongest oxidizing agent. Okay? It's going to be the strongest oxidizing agent. So no, the iodate ion will not oxidize the chlorine because chlorine is a stronger oxidizing agent than the iodate. So again, the more positive, the stronger the oxidizing agent. The more negative, the stronger the reducing agent. Now that's something that you would just have to memorize. Can anybody tell me another way that you could have solved this problem? Can somebody tell me another way that we could have solved this problem that would have actually been easier? Couldn't we just use this formula? What occurs at the cathode, oxidation or reduction?
Reduction.
Right? So this is reduction. This is oxidation. So we're talking about oxidizing chloride. So that must mean that the chlorine was this anode right here, right? So that would have been plus 1 point, whoops, I'm sorry, that was the wrong value. That's over here, right? So it's minus this 1.36 volts, since that is the oxidation. We're talking about oxidizing the chloride, which means that the iodate must have been the reduction, which is plus 1.2 volts. That would have given us a value of negative 0.16 volts. So is this reaction spontaneous? No, right? Negative, non-spontaneous. So there's another reason we could say that the I3 will not, right? Will not oxidize the chloride. Any questions about that? Okay, let's try it again. This time it says, will the dichromate ion oxidize chromium-3 ion in acidic solution under standard conditions? Okay, well, let's see. I need to look up dichromate. So again, I'm going to go through my tables. Now, the polyatomic ions are harder to pinpoint whether they're going to be positive or negative. So we're just basically going to have to go through. So I'm looking for dichromate and chromium-3. So I'm looking for both of those. So I'm going to go through here and I'm looking for dichromate and chromium-3. What? There's a chromium-3. Right there's a chromium-3. So let me write that down real quick. So we have Cr3 plus 3 electrons going to Cr solid with a reduction potential of negative 0.73 volts. Okay, so that was that one. But let's keep going. Oh, wait a minute. There's another one. That's chromium-3 plus 2 electrons. No, plus 1 electron going to chromium-2 plus. And that has a negative 0.50 volts. Okay, let's keep going. Let's see. Okay, nothing there. There's our dichromate. So that is this Cr2, O72 minus plus 14 hydrogen ions plus 6 electrons going to 2 chromium-3 plus 7 H2O liquid, and it has a reduction potential of positive 1.33. And then again, I just want to make sure that there's no more chromium or dichromate, and there is not. So that's it. Those are all the reactions that I'm aware of. Could you eliminate any of these reactions? Now think about it, when we balance this thing, we're not going to have, it says, will it oxidize chromium-3 plus? Well, chances are I don't see any chromium-2 plus there. But I'm going to show you that it doesn't even matter that you don't recognize that, okay? So let's look at it, right? So we want to know, will dichromate oxidize chromium-3? Well, what is the stronger oxidizing? What is the strongest oxidizing agent here? What is the strongest oxidizing agent?
Dichromate.
Yeah, right. It has the most positive. So these would represent our oxidizing agents. It's always going to be the reactants. The dichromate has the highest positive value. So that is my strongest oxidizing agent. So will dichromate oxidize chromium-3? Or chromium-2, I'm sorry, chromium-2. Oh, there was a chromium-2, right? So we didn't even need this reaction because it is asking for chromium-2 specifically. This doesn't even contain chromium-3, so we can eliminate that. But again, you can see that it actually didn't matter, because since this is positive, that's the strongest oxidizing agent, then the answer is yes. Yes, it will, right? Yes, it will. And again, we could have done it similarly this way, right? We could have said E cell is equal to the cathode minus the anode. Again, we know that reduction occurs at the cathode and oxidation occurs at the anode. So it wants to know, will dichromate oxidize chromium-2? So oxidation occurs at the anode, so that means the chromium must have been that one. So that would have been the negative 0.5 volts. And then the other one had to be the 1.33 volts. We would subtract the two, okay? And that would give me a value then of 1.83 volts. So it is positive, therefore spontaneous. And so again, yes, it would have oxidized it. And we could have seen that if we would have put in this value, the negative 0.73, it too would have said it was positive. So even if you're unsure which species, generally it doesn't matter. Okay, any questions with recognizing, oxidizing, and reducing agents?